All right, let's dive right in. Today, we're going to take a look at what's often called the mother branch of all engineering. It's the invisible blueprint behind almost every single physical, moving thing you can imagine. We're talking, of course, about mechanical engineering. So, let me ask you a question. What does a massive rocket tearing its way through the atmosphere have in common with a tiny robot performing surgery with unbelievable precision? Or, for that matter, with a sleek electric car gliding silently down the highway? I mean, they seem worlds apart, right? But they all share the exact same engineering DNA. And that shared DNA, well, that's mechanical engineering. There's a reason people call it the mother branch. It's because it really does provide the fundamental blueprint for our entire physical, moving world. So what is it exactly? To put it simply, mechanical engineering is the art and science of using physics and materials to make things work. We're talking about everything from the tiniest gear in a watch to the largest spacecraft ever built. If it's a system designed to move, to use energy, or to get a job done, you can bet a mechanical engineer was there from the very beginning. But how do they actually pull all that off? What's in their secret toolkit that lets them build our world? Well, every mechanical engineer has to master a set of core principles. Think of these as their essential gear. It all kicks off with statics and dynamics, which is really just the science of forces. So picture a bridge. Statics is what tells you how it can stand firm against gravity, wind, and traffic. Now, picture a Formula One car. Dynamics is what explains how that car can just hug a corner at 200 miles per hour without flying off the track. It's the absolute starting point for making sure things don't fall down or fly apart. Next up in the toolbox is thermodynamics. This is all about energy, heat, and power. It's the science that unlocks the energy and fuel to make an engine roar to life. But it's also the very same principle that lets your air conditioner move heat from inside your house to the outside on a hot day. It's all about controlling energy to do useful things for us. Then you've got fluid mechanics. This one governs pretty much everything that flows, and that means liquids and gases. It's how engineers design the perfect curve of an airplane wing so that air generates lift, but it's also how they figure out how to pump oil across an entire continent through a pipeline with as little friction as possible. It's the mastery of flow. Of course, none of that matters if your brilliant design just breaks, and that's where strength of materials becomes absolutely critical. Engineers obsess over this stuff, how much a material can bend, how much it can stretch, or how much it can twist before it fails. This is what guarantees a skyscraper's beams won't buckle, and, more importantly, that a car's frame will actually protect you in a crash. You know, a great design on a computer screen is totally useless if you can't actually build it in the real world. That's where manufacturing processes come in. This is the part of the toolkit for turning a digital blueprint into a physical thing, whether that's by doing something traditional like welding steel, or something cutting edge like using a 3D printer to create a complex part, layer by tiny layer. And in our modern world, we have to add mechatronics to the list. This is where physical machinery gets a brain. By blending classic mechanics with the precision of electronics and computer control, we get all the smart systems that are around us today, from the anti-lock brakes in your car to the amazing industrial robots that assemble it. So, that's the toolkit. Those are the core principles. Now let's get to the fun part and see what happens when you put all of that into practice and actually start building our modern world. And wow, the impact is just staggering. I mean, just look at the range here. You see it in the cars we drive, the planes we fly, the energy that powers our homes, and even in the medical technology that literally saves lives. Mechanical engineering isn't just one industry. It's the foundational layer for almost all of them. Let's take aerospace, for example. A mechanical engineer is the one designing a rocket engine with enough raw thrust to punch through Earth's gravity. They're figuring out how to build a satellite frame that's super lightweight but can still survive the harsh vacuum of space. And they're the ones who designed the rugged suspension system on that rover exploring Mars right now. Or how about its impact on our health? This is where it gets really personal. Mechanical engineering is behind robotic hands that can feel, artificial hearts that can pump blood, and those incredibly steady, precise surgical arms that allow surgeons to perform what really look like miracles. It's engineering in service of the human body. And of course, you see it every single day. Just think about the car you drive. Pretty much every part of it, from the engine or the EV battery system to the chassis it's built on, and most importantly, the life-saving crash structures, it's all a product of mechanical engineering. So this field has clearly built our present, but it is definitely not standing still. For this last part, let's look ahead to the next frontier and see how this historic discipline just keeps on evolving. The future is really all about integration.
Mechanical engineering is merging with artificial intelligence to create machines that can actually learn and adapt on their own. It's at the absolute forefront of sustainability, designing more efficient wind turbines and revolutionary new solar power systems. And it's using incredible new materials to build things that were once physically impossible, making everything stronger, lighter, and more capable than ever before.
When you think about it, from the very first steam engine all the way to the rockets that took us to the moon, mechanical engineering has always been about one thing: turning imagination into physical reality. So the only real question left is, as our world keeps evolving, what will they build next?